Hi, this is Fred Lim from Facebook, and in this video I'm going to present our work on fast dimensional analysis for root cause investigation in a large-scale service environment. This has been a highly cross-functional work between me, Kayer, Nikolai, Mihai, Seunghak, and Shuram, and I definitely appreciate the opportunity to work with this group of awesome people. Facebook has been scaling up. We have a lot of users. Globally, there are more than 2.8 billion people using Facebook, WhatsApp, Instagram, and Messenger each month. Especially now with the COVID situation, some of the services on Facebook have become even more critical to our everyday lives and health. For that, we have been building infrastructure. On this picture, you can see some of the announced data centers. And fun fact, one of the buildings here is actually as long as the Empire State Building is high. And on some sides, there are multiple buildings like this. We have also been refreshing our fleet with newer hardware and of course firmwares to keep up with the demand and for better reliability. With the constant introduction of new hardware and software configurations, however, hardware sustaining has become increasingly complex. So in addition to more and newer hardware and software, we also need better tooling to help us sustain the fleet efficiently. And that is what motivated us for this work, as root cause analysis is the core for hardware sustaining. So here's the agenda of this video. We will first go through what production service environments are like nowadays. Then we will give some examples and discuss the state of the art for root cause analysis in production. Then we present the proposed fast dimensional analysis framework followed by experimental results. In the paper, we also presented the production setup for 4 other use cases, but here we won't have time to cover those in this video. So really, what's in a data center? Well, in short, mainly tons of servers, storage, and network switches. Typically, we want to maintain a high server to administrator ratio, and that is often achieved with autonomous systems. In an interview in 2013, our number of server to admin ratio was reported to be greater than 20K. So here let's look at some of the goals and the systems. One of the top level goals for our fleet is to be run at high utilization, meaning whatever resource we're having, we're using them properly as much as possible. And the system for that will be the scheduling system, and that's, for example, like Borg from Google or Apollo from Microsoft. In general, people have found that scaling out is better than scaling up in most cases. The second top level goal will be high availability, meaning whatever resource we have, they are as available as possible to run the services and applications that we have. And that would depend on the remediation systems, meaning whenever the server is going down, we can remediate the problem very quickly and put it back online to serve the application. Systems like Autopilot from Microsoft or FBAR from Facebook are the remediation systems for this. So what does root cause analysis really mean in production? Let's look at an example. Let's say we found that the spike of unexpected server events was triggered by or when scheduler version V puts application A on server model M that are running kernel version K. So there are multiple components here. Scheduler version V, it could be a dimension or a feature from the tooling log because scheduler is part of the tooling systems. Application A will be a feature or a dimension from the software log, and it could be the application name or the expected load or the routing of the traffic, for example. Server model and kernel versions will be from the hardware log because they are part of the server configuration. And this type of logs, hardware, software, and tooling are really the 3 major logs that you can find in a production environment. Looking at this example, it's easy to see that logging in structured tables is the key to make this easy. If we have free-form text logs, you will have to parse this information out with regular expression or maybe natural language processing, for which there are always uncertainties because people may change the way they log the same message then you will have to update your regular expression or your natural language processing model. Some of the prior root cause analysis work. In production, the most naive root cause analysis people would do is to group the entities by order dimensions. But this could be very expensive computationally. So just recall that the three types of logs, hardware, software, and tooling, each log could have potentially hundreds to thousands of dimensions. And so the combination of this can easily give you millions of combinations, and it would be very hard to compute all of them and very hard for human to review the result. There have been decision tree based methods. The advantage of this is that it provides very good visibility in the features, like how they are being used at each node for making the decision. The disadvantage of this is that it's hard to tune and interpret as the trees grow, or even if we have an ensemble model, as each of this tree grow, it's hard to tune. Another way to do this is Stuco. Stuco could miss important associations when pruning while growing the tree. We have more discussions on this in the paper, but I won't have time to go through the details here. The fourth approach will be the a priori algorithm, which indeed finds all of the association rules. The only downside is that it's computationally expensive. Here's our proposed framework for fast dimension analysis. Our requirement here is really simple. We want to find critical patterns in near real time across millions to billions of entries from our software, hardware, and tooling logs. The first step is a preprocessing step. We allow the subject matter experts to exclude less relevant features to improve the performance. We automatically exclude features with very low or very high cardinalities. So features with very low cardinalities could be a feature that has the same value for everything in the table. So that means nothing to the analysis really. Features with very high cardinalities could be timestamps or say job ID for the applications. And these values are so unique that it wouldn't help to find commonalities across the jobs, but keeping them in the data set would significantly slow down the analysis. We also pre-aggregate with Scuba, which is a real-time in-memory database for large-scale data at Facebook. Because we found that in production, a lot of the entries are actually duplicates, say this exactly same job getting retried every 5 seconds, for example. And we really only need one of this job and maybe another column, which is the count of these jobs in the table for our analysis. In production, the pre-aggregation step could reduce the data size by 200 to 500 times, which would significantly improve the scalability of our fast dimension analysis framework. Runtime-wise, including the pre-aggregation operation time, this could reduce the runtime by 10 to 20 times. For the frequent pattern mining, we use FP growth, which is an improvement on top of a priori algorithm. And here we are trying to mine all the frequent patterns that appear in the target dataset. After this, we do some pattern filtering. So we filter with a lift, which I'll introduce in the next slide. And we have additional duplication steps to improve the interpretability. So let's do a comparison between a lift and a more traditional metric confidence. Let's think about Y as a status, say the job status being failed, and X as an attribute, for example, kernel version v1. Let's first introduce support. Support is measuring that out of all the jobs that have failed, how many of them were running on machines with kernel version v1. This is measuring how common kernel version v1 is among all the failures, but it does not tell us anything about how common kernel version v1 is among all the successful jobs. So maybe kernel version v1 is just common across all the jobs, and that would still give us a very high support value. Confidence, on the other hand, measures that out of all the jobs running on machines with kernel version v1, how many of them have failed. This is measuring how common it is for jobs running on machines with kernel version v1 to fail. Similarly, it does not measure how common it is for jobs not running on kernel version v1 to fail. So maybe all the jobs are just failing anyways, but we will have a high value of confidence value. Finally, lift measures how much more likely that x and y will happen together relative to if they are independent. So lift is a measurement or a measure of how kernel version v1 can help distinguish between failing and successful jobs, and vice versa. Hence, it is less misleading compared to support and confidence. Before we start the experimental results, let's first define a few terms, items and item sets. Let's look at the example that we had before, and here, each of these dimensions are called an item. Collectively, they are called an item set. So an item set is a collection of features that would describe a population of samples. In our experimentation, we used two production data sets. The first data set logs anomalous server event, which we will refer to as ASE later. It has millions of events. Each event is described by 20 features, which expands to 1,500 distinct items. The second data set logs server requests, which also has millions of events, and each event is described by 50 features, which expands to 500 distinct items. In this first chart, we can see that FP growth is constantly faster than a priori, regardless of the number of item sets. But compared to a multi-threaded version of a priori, FP growth can be slightly slower when the number of item sets is very small. Now let's look at the runtime reduction from the pre-aggregation step using Scuba. With the pre-aggregation, you can see the runtime could be reduced by 10 times or 20 times depending on which dataset we're looking at. So it also depends on the nature of the dataset. Now let's look at the interpretability of the analysis. On the left-hand side, we have the number of association rules reported versus minimum lift, which is the variable in our configuration for the ASE dataset. On the right-hand side, we have the same thing for the SR dataset. The red triangles mark when the target item sets are captured for each of these problems. So on the left-hand side for ASE dataset, we see the target item set was captured when there are fewer than 10 association rules or item sets reported. On the right-hand side for SR dataset, the target item set was captured when there are fewer than 20 item sets or association rules reported. And this is very easy for people to review because you only need to look at no more than 20 item sets to find one that's associated with the biggest issue in this data set. Note that our additional duplication step that I mentioned before removed more than 90% of the reported item sets, and that's what made this so scalable for the human review step. In conclusion, we presented a scalable framework with results validated on real datasets in a large-scale production environment. In the paper, we also demonstrated the production setup and experimental results for other datasets that include anomalous hardware and software configurations, anomalous service interactions, auto-remediation failures, and SSH logs. I didn't have time to cover those in this video, but they are presented in the paper. We are now exploring to extend the framework to temporal analysis and continuous variables, as well as root cause analysis for text reports using natural language processing. Thank you.